March 7th, 1943. Hauptmann Ernst Richter kneels in frozen mud outside Kharkov, examining what appears to be a length of drainage pipe abandoned in a hastily evacuated Soviet position. The tube weighs perhaps 6 kilograms, crude steel construction with a wooden shoulder stock and iron sights that wouldn't look sophisticated on a hunting rifle. For 2 years, German anti-tank doctrine had pursued mathematical perfection through increasingly massive gun systems, the 7.5 centimeter Pak-40 requiring 6 specialists and a 3-ton truck, the monstrous 8.8 centimeter Flak requiring 9 crew members and weighing over 7,000 kilograms in firing position. This American contraption, found among Soviet equipment captured during the Third Battle of Kharkov, looked like something fabricated in a basement workshop by an amateur metalworker. Yet, stamped into the aluminum housing, barely visible beneath accumulated grime, were English markings that would force German ordnance experts to confront uncomfortable truths about portable firepower. General Electric, Bridgeport, Connecticut. M9A1 rocket launcher, 2.36-inch. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Back at the Wehrmacht testing facility outside Poltava, Oberst Wilhelm Dornberger examines the captured launcher with the institutional skepticism that had guided German weapons evaluation throughout the war. Americans build automobiles and kitchen appliances with admirable efficiency, but precision anti-tank weaponry requires European engineering discipline that their industrial culture fundamentally lacks. The weapon's very simplicity seems to confirm every assumption about American military amateurism. 3 days later, when they load the first captured rocket and fire at a disabled Soviet 34 positioned 50 meters downrange, the shaped charge warhead punches completely through 120 millimeters of sloped frontal armor. The explosion exits through the tank's rear plate, leaving a hole large enough to pass a man's fist. The testing range falls absolutely silent. Every German engineer present understands immediately what they're witnessing. This primitive tube, weighing less than a single round for their Pak-40, has just delivered anti-tank penetration exceeding their most powerful towed guns. Everything German weapons development believed about the relationship between weight, complexity, and battlefield effectiveness has been proven fundamentally wrong by a device that appears to violate every principle of rational ordnance design. The morning sun cast long shadows across the Ukrainian steppe as Hauptmann Richter picked through the abandoned defensive positions that Soviet forces had evacuated during the previous night's withdrawal. The temperature hovered near freezing, typical for early March in this region, and the ground remained hard with frost that would transform into impassable mud within weeks as spring temperatures arrived. Scattered equipment told the familiar story of hasty retreat under pressure. Ammunition crates broken open and partially emptied, personal effects discarded to reduce load during forced march. A field telephone with its wire cut, preventing German intelligence from tracing communication lines back to Soviet command posts. But it was the metallic object protruding from a foxhole that caught Richter's attention, something unfamiliar among the standard debris of modern warfare. He approached cautiously, mindful of booby traps that Soviet engineers routinely left behind during withdrawals, but this appeared to be simple abandonment rather than deliberate sabotage. The device measured approximately 140 centimeters from end to end, constructed from what appeared to be standard industrial steel tubing with minimal external features. A wooden shoulder stock attached to the rear, basic iron sights mounted atop the tube, and a simple trigger assembly connected to what looked like electrical contacts rather than conventional firing mechanisms. Richter lifted the tube carefully, noting its surprisingly light weight, perhaps 6 kilograms, possibly 7 with whatever internal components remained hidden within the steel construction. For comparison, German infantry anti-tank weapons like the Panzerbüchse 39 rifle weighed nearly 16 kilograms and fired armor-piercing rounds that had proven increasingly ineffective against modern Soviet tank armor. This tube weighed less than half that amount, yet appeared designed for some anti-tank purpose based on its substantial bore diameter. The manufacturer markings stamped into an aluminum plate near the rear of the tube identified origins that immediately raised questions about how American military equipment had reached Soviet positions deep in Ukrainian territory. General Electric Corporation, Bridgeport, Connecticut, USA. Additional markings indicated military designation: M9A1, rocket launcher, 2.3, 6-inch, along with contract numbers and production dates suggesting manufacture during 1942. Richter had encountered American weapons before, primarily small arms captured from British forces in North Africa, who received equipment through Lend-Lease arrangements. But anti-tank systems represented specialized military technology that few nations had mastered effectively. The apparent simplicity of this American launcher seemed inconsistent with the sophisticated engineering required for defeating modern armor protection. German anti-tank doctrine had evolved through painful experience on the Eastern Front, where Soviet 34 tanks had rendered obsolete virtually every existing German anti-tank weapon during the summer of 1941. The Pak-36, which had effortlessly destroyed Polish and French armor during the early war period, bounced 3.7 centimeter rounds harmlessly off the 34's sloped 45mm frontal armor. German response had followed predictable engineering logic, develop more powerful guns, firing heavier projectiles at higher velocities to defeat improved armor through superior ballistic performance. The resulting Pak-40 represented mathematical elegance, translated into steel and precision machinery. 7.5 centimeter caliber firing tungsten cord ammunition, capable of penetrating 132 millimeters of vertical armor plate at 500 meters range. The complete system weighed 1,425 kilograms, required transport by Opel Blitz 3-ton truck, and needed 6 trained specialists for proper combat operation. Positioning the gun for engagement required approximately 20 minutes under ideal conditions, longer when tactical circumstances demanded careful camouflage or protective earthworks. This American tube, by contrast, appeared designed for operation by a single soldier with minimal training and no supporting equipment, beyond the ammunition itself. The contrast seemed almost absurd to someone familiar with German ordnance development philosophy, where effectiveness and complexity were considered inseparable. Richter examined the firing mechanism more closely, noting its elementary construction. A battery compartment containing what appeared to be standard dry cells, similar to those used in flashlights. Simple electrical contacts connected to the trigger assembly through basic copper wiring, with no apparent precision components or delicate mechanisms that might require careful adjustment or maintenance. Everything about the weapon violated fundamental principles that German engineers had established through decades of systematic weapons development. No complex recoil absorption systems to manage firing forces, no precision optical sights for accurate range estimation, no sophisticated mounting hardware to ensure stable firing platform. The device looked like something that agricultural machinery manufacturers might produce rather than specialized ordnance contractors. 2 additional items lay scattered near the abandoned launcher. Cylindrical objects wrapped in protective canvas that Richter carefully unwrapped to reveal what were obviously the ammunition designed for this peculiar weapon system. Each rocket measured approximately 60 centimeters in length, with a distinctive shape that immediately identified its purpose. A pointed nose cone made from aluminum or similar lightweight metal, a cylindrical body section containing what appeared to be explosive filling, and a rear section with stabilizing fins folded against the body for storage. The rockets weighed approximately 1.5 kilograms each, remarkably light compared to German anti-tank ammunition. A single 7.5 centimeter Pak-40 round weighed 6.8 kilograms, nearly 5 times heavier than these American projectiles. Yet the shaped charge warhead design, clearly visible through the aluminum nose cone, suggested these lightweight rockets might achieve armor penetration through entirely different physical principles than German kinetic energy penetrators. Richter had read technical intelligence reports describing shaped charge technology, a relatively new approach to defeating armor that utilized explosive physics rather than kinetic impact. The principle involved focusing explosive force into a narrow jet of superheated gas and metal particles that could penetrate armor through thermal and pressure effects, rather than simple momentum transfer. German engineers had experimented with shaped charges in specialized applications, but considered the technology too unreliable for primary anti-tank weapons. The American approach, apparently, involved betting their entire portable anti-tank capability on this exotic technology, rather than proven conventional penetrators. The decision seemed characteristic of American engineering philosophy that prioritized novel solutions over established methodologies, sometimes with remarkable success, occasionally with spectacular failure. Which category this launcher represented remained to be determined through systematic testing under controlled conditions. Richter secured the launcher and both rockets in his command vehicle for transport back to Wehrmacht testing facilities, where proper evaluation could occur. The discovery represented potentially significant intelligence regarding American anti-tank capabilities being transferred to Soviet forces through Lend-Lease programs. Understanding these capabilities meant understanding what German armor would face not only on the Eastern Front, but eventually on Western fronts, when American forces entered direct combat against Wehrmacht units. The journey to the testing facility at Poltava required 12 hours through Ukrainian countryside, showing increasing evidence of spring approaching. Roads that had been frozen solid during winter campaigns were beginning to soften, creating the notorious Rasputitsa mud season that would effectively halt mechanized operations for weeks until ground hardened again. This seasonal reality shaped every aspect of Eastern Front warfare, creating brief windows for offensive operations between winter cold and spring mud, then again between summer drought and autumn rain. At Poltava, Oberst Wilhelm Dornberger commanded Wehrmacht ordnance testing operations for the entire southern sector of the Eastern Front. At 52 years old, Dornberger represented traditional German military engineering culture, methodical evaluation based on quantifiable performance metrics, systematic documentation of all findings, and institutional skepticism toward enemy equipment claims that seemed inconsistent with established technical understanding. His evaluations had exposed numerous examples of Soviet equipment that appeared formidable through propaganda photographs, but proved inferior upon detailed examination. Dornberger examined the captured American launcher with characteristic Prussian disdain when Richter presented it the following morning. The Wehrmacht testing facility occupied former Soviet military grounds that German forces had captured during the summer of 1942, now converted into comprehensive evaluation infrastructure, supporting ordnance testing across all equipment categories. Armor plate testing ranges extended nearly 2 kilometers from the main facility buildings. Ballistic chronographs measured projectile velocities with precision equipment salvaged from German universities. Machine shops provided capability to disassemble and analyze captured equipment down to individual components. Rocket launcher, anti-tank, M9A1, Dornberger read from the American technical markings, his voice carrying professional skepticism developed through decades of weapons evaluation. Americans excel at mass production of consumer goods, automobiles, refrigerators, entertainment systems, but precision military equipment requires engineering discipline that their industrial culture fundamentally lacks. This appears consistent with expectations for American military equipment, adequate for garrison purposes, but unsuitable for serious combat against professional military forces. Richter remained silent, though something about the launcher's elegant simplicity troubled him. His engineering education at Technical University of Berlin had taught him to recognize sophisticated solutions disguised as simple implementations. The more he studied this American design, the more he suspected they were missing something fundamental about its approach to portable anti-tank warfare. German doctrine had pursued effectiveness through complexity and precision. This American system appeared to have achieved effectiveness through radical simplification and novel physics. The first rocket arrived from storage that afternoon, carefully transported under guard due to explosive hazards, inherent in captured ammunition of unknown condition. The projectile's construction revealed surprising sophistication hidden within its crude external appearance. The warhead section contained precisely machined copper cone positioned apex forward within the explosive charge, the critical component for creating shaped charge penetration through the Monroe effect. German shaped charge experiments had required similar precision manufacturing, suggesting American ordnance industry possessed metallurgical capabilities exceeding their reputation for crude mass production. Dornberger ordered immediate testing against a captured Soviet 34 positioned 50 meters from the firing line, the standard engagement range for German anti-tank guns during defensive operations. The tank had been disabled during previous combat, its engine and transmission destroyed by internal fire, but the armor remained intact and suitable for penetration testing. The 34's frontal armor consisted of 45mm steel plate sloped at 60 degrees from vertical, creating effective thickness of approximately 90mm through geometric principles. Additional applique armor welded to the glacis during field modifications increased protection to nominal 120mm effective thickness. This represented formidable protection that German 3.7cm and 5cm anti-tank guns could not reliably penetrate at any practical combat range. Even the Pak-40, with its 7.5cm tungsten ammunition, achieved penetration only with careful shot placement against specific armor sections. For this lightweight American tube to defeat such protection seemed physically impossible according to every principle of ballistic engineering that German ordnance understood. The test firing would be conducted by Feldwebel Otto Brecht, an experienced gunnery instructor who had trained on virtually every German anti-tank system in the service. Brecht examined the launcher with obvious skepticism, noting the absence of familiar features that characterized proper military weapons. No recoil damping system to manage firing forces. No complex sight picture requiring careful alignment. No precise leveling mechanisms to ensure accurate trajectory calculations. The American weapon appeared designed for operation by soldiers with minimal technical training, an approach that German doctrine considered fundamentally flawed. Brecht shouldered the launcher, noting how the wooden stock positioned weight distribution naturally against his shoulder and chest. The iron sights provided crude aiming reference, essentially identical to rifle sights, requiring simple alignment between front and rear posts. American technical documentation captured with the launcher indicated proper procedure: aim center mass of target, squeeze trigger smoothly, maintain position through rocket motor burn, no range estimation tables, no windage, corrections, no elevation adjustments for distance. The simplicity seemed almost insulting to someone trained in German gunnery precision. At Dornberger's command, Brecht aligned the sights on the 34's turret front, squeezed the electrical trigger, and immediately stepped sideways as the rocket motor ignited with a sharp whoosh of expanding gas. The projectile accelerated down the launch tube, stabilizing fins deploying automatically as it cleared the muzzle, and streaked toward the target trailing white smoke from its solid fuel motor. Flight time to 50 meters measured perhaps half a second, far too brief for conscious tracking or correction. The impact against the 34's frontal armor produced a sharp crack that echoed across the testing range, distinctly different from the metallic clang of armor-piercing shot-striking steel. For a moment, nothing seemed to happen. Then Richter noticed smoke beginning to vent from the tank's interior through every opening, hatches, vision ports, the hole where the machine gun had been removed. The shaped charge warhead had functioned exactly as designed, converting its 1.5 kilograms of explosive into a focused jet of superheated particles, traveling at approximately 8,000 meters per second. Dornberger approached the 34 slowly, followed by his engineering staff carrying measuring equipment and documentation cameras. The entry hole on the frontal armor measured 62 millimeters in diameter, surrounded by minimal spalling or secondary damage. More significantly, inspection of the tank's interior revealed the penetration had continued completely through the fighting compartment, through the rear armor plate, and exited the vehicle entirely. The shaped charge had defeated 120 millimeters of effective armor protection as casually as German guns penetrated thin reconnaissance vehicle plating. The silence that followed lasted nearly a full minute, as every German and engineer present processed what they had just witnessed. Richter found himself checking calculations mentally, verifying that he had correctly observed what physical evidence confirmed. This primitive American tube, weighing 6 kilograms, had just delivered anti-tank penetration exceeding their Pak-40, which weighed 1,425 kilograms and required 6-man crew for operation. The mathematics were undeniable. The implications were devastating to German anti-tank doctrine. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. "Prepare the second rocket immediately," Dornberger ordered quietly, his voice carefully controlled. "I want to verify this result under documented conditions before filing any preliminary reports." The institutional caution was characteristic of German military bureaucracy that demanded comprehensive data before reaching conclusions that might challenge established doctrine. But Richter recognized the defensive posture underlying Dornberger's measured response. They had just witnessed American engineering solving portable anti-tank warfare more effectively than Germany's finest ordnance designers, and the admission would require irrefutable documentation before Wehrmacht High Command would accept such uncomfortable conclusions. Over the following week, systematic testing would reveal the full extent of German miscalculation regarding portable anti-tank technology. But already, standing beside the smoking 34 with its impossible penetration hole, Richter understood they were witnessing something more significant than superior American equipment. They were witnessing the collision between German engineering philosophy that pursued perfection through complexity and American industrial thinking that achieved effectiveness through radical simplification. The Americans hadn't built a better anti-tank gun. They had reconsidered the fundamental question of how to provide infantry units with armor-defeating capability, and their answer violated every assumption. German ordnance doctrine held sacred. Weight didn't matter if the weapon could be carried by a single soldier. Precision didn't matter if the shaped charge worked effectively across typical combat ranges. Complexity didn't matter if simple systems proved reliable under battlefield conditions. German engineers had been asking the wrong questions entirely, and the Americans had just demonstrated what happened when someone asked better ones. The captured launcher sat on its wooden rest beside the punctured 34, an unassuming steel tube that represented nothing less than a revolution in portable firepower. Within months, similar weapons would be appearing on every front where American forces engaged German armor. Within a year, German industry would be desperately attempting to copy American design principles, while simultaneously dismissing them as theoretically unsound. The irony would be lost on no one who understood what had just occurred at this Ukrainian testing range. Germany's precision engineering culture had been defeated by American industrial pragmatism, and no amount of mathematical elegance could overcome the fundamental effectiveness of shaped charge physics married to mass production capability. The morning testing session concluded with Dornberger ordering comprehensive documentation of all findings before proceeding with additional trials. Photography specialists captured detailed images of the penetration damage from multiple angles. Metallurgical experts collected armor samples from around the entry and exit holes for laboratory analysis. Ballistic engineers measured crater dimensions and calculated penetration mechanics based on observable evidence. The methodical German approach to weapons evaluation would generate hundreds of pages of technical data over the coming weeks, but the fundamental conclusion was already unavoidable. American engineers had solved portable anti-tank warfare through an approach so radically different from German methodology that Wehrmacht ordnance experts had failed to even recognize it as a legitimate solution until confronted with empirical proof of its effectiveness. Richter spent the afternoon examining the launcher's internal components after Dornberger authorized limited disassembly for technical intelligence purposes. The battery compartment revealed standard American dry cell construction, readily available commercial components rather than specialized military equipment. The electrical firing circuit consisted of simple copper wiring, connecting battery terminals to an igniter element that would be inserted into the rocket motor during loading procedures. Total parts count for the entire firing mechanism numbered fewer than 20 discrete components, several of which appeared to be standard hardware store items, rather than precision-manufactured military parts. By comparison, German anti-tank guns incorporated thousands of precision components requiring specialized manufacturing, equipment, and skilled assembly labor. The Pak-40's recoil system alone contained more moving parts than the entire American launcher. Breech mechanisms demanded tolerances measured in hundredths of millimeters. Optical sights required hand-fitting by trained technicians. Every aspect of German anti-tank gun design reflected commitment to engineering excellence that American designers had apparently considered irrelevant to battlefield effectiveness. The rocket motor assembly revealed equally surprising simplicity in its construction approach. Solid propellant grain cast directly into thin-walled steel tube with minimal internal complexity. Nozzle design consisting of basic convergent shape without the sophisticated expansion sections that German rocket engineers considered essential for efficient thrust production. Igniter element positioned for reliable initiation without requiring precise alignment or careful installation procedures. Everything about the design prioritized reliable function over optimal performance, adequate thrust over maximum efficiency, consistent ignition over theoretical perfection. German rocket development, by contrast, had pursued mathematical optimization of every parameter. Propellant grain geometry calculated to maintain constant thrust throughout burn duration. Nozzle expansion ratios precisely matched to altitude and velocity conditions. Igniter systems incorporating redundant elements to ensure function under all environmental circumstances. The result was rocket motors that performed superbly under test conditions, but required careful handling and environmental protection to maintain reliability in combat use. The American approach accepted performance penalties inherent in simplified design to achieve reliability under conditions that would disable more sophisticated systems. Their rocket motors produced lower specific impulse than German designs, but functioned reliably after rough handling, temperature extremes, and moisture exposure that would render German rockets inoperable. They achieved perhaps 80% of theoretical performance, but maintained that performance level across 100% of operational conditions. German rockets achieved 95% of theoretical maximum, but only under the narrow environmental parameters their precision demanded. As evening approached, Richter compiled preliminary observations for Dornberger's review before formal testing resumed the following morning. His engineering analysis identified three fundamental areas where American design philosophy had produced solutions superior to German approaches, despite apparent technical inferiority. First, the shaped charge warhead eliminated the velocity requirements that dominated conventional anti-tank gun design. German kinetic penetrators required extremely high muzzle velocities to defeat armor through momentum transfer, necessitating large propellant charges, heavy gun tubes capable of withstanding firing pressures, and sophisticated recoil systems to manage the forces involved. The American-shaped charge achieved penetration through thermal and pressure effects that were essentially independent of projectile velocity. The rocket motor needed only to propel the warhead across combat ranges at speeds sufficient for stable flight, perhaps 150 meters per second, compared to the 800 meters per second required for German armor-piercing shot. This single principle eliminated 90% of the complexity inherent in conventional anti-tank guns. Second, the launcher's disposable approach to accuracy eliminated the precision manufacturing required for conventional firearms. German anti-tank guns demanded precisely machined barrels, carefully aligned sights, and stable mounting platforms to achieve the accuracy necessary for engaging targets at maximum range. The American launcher accepted reduced accuracy as inherent limitation of its simple construction, compensating through shaped charge effectiveness that remained lethal across a wide impact area rather than requiring precise shot placement against specific armor sections. Finally, the electrical firing system proved more reliable than conventional percussion mechanisms under field conditions. German anti-tank guns used sophisticated firing pins, springs, and triggering mechanisms that required regular maintenance and could be disabled by mud, ice, or carbon fouling. The American electrical system functioned reliably as long as battery power remained available, and batteries proved far more resistant to environmental degradation than precision mechanical components. Each design decision represented American willingness to sacrifice theoretical performance for practical reliability, accepting limitations that German engineering culture considered unacceptable compromises. The cumulative effect was a weapon system optimized for actual combat conditions rather than test, range performance metrics. German ordnance had pursued perfection. American ordnance had pursued adequacy at scale. In total warfare, adequacy multiplied by availability was proving superior to perfection limited by complexity. The comprehensive testing program commenced the following Monday with methodical precision that characterized all German military evaluation protocols. Oberleutnant Klaus Weber arrived from Krupp Works in Essen, temporarily assigned to assess manufacturing implications of the American design. Weber's production engineering background provided crucial perspective that complemented Richter's technical analysis and Dornberger's operational assessment. Where Richter understood ballistic principles and Dornberger evaluated tactical applications, Weber recognized industrial strategy underlying every design decision visible in the launcher's construction. Test series. Alpha focused on penetration characteristics across varying armor configurations representative of German, Soviet, and British armored vehicles. Weber had arranged delivery of steel plate samples ranging from 20 mm to 150 mm thickness, including both homogeneous armor and face-hardened variants used in different applications. Each plate would be tested at precisely measured distances, 25, 50, 75, and 100 meters, with all environmental conditions documented for correlation analysis. Temperature and humidity were recorded at 15-minute intervals throughout testing operations. Wind speed and direction were measured using calibrated meteorological instruments positioned at firing line and target locations. Barometric pressure readings documented atmospheric density that might affect rocket motor performance. German thoroughness demanded that every conceivable variable be controlled and quantified to ensure test results reflected genuine weapon performance rather than environmental anomalies. The first series of shots against 20 mm plate at 25 meters produced results that seemed almost excessive for such light armor. The shaped charge warhead punched through the steel with such violence that the exit hole measured 80 mm diameter, surrounded by petaling and fragmentation that would prove lethal to vehicle crew even without direct penetration. Richter measured and photographed the damage pattern, noting how the Monroe effect had converted explosive force into focused thermal energy with remarkable efficiency. Successive trials against progressively thicker armor revealed the shaped charge's essential characteristic. Penetration performance remained largely independent of armor thickness within tested ranges. 40 mm plates representing German Panzer III frontal armor offered no meaningful resistance. 60 mm sections typical of Panzer IV turret faces were defeated as casually as lighter protection. Even 100 mm plates, approximating Tiger tank armor, showed complete penetration with exit holes measuring 50 to 60 mm diameter. The data formed an undeniable pattern that challenged fundamental assumptions about armor protection underlying German tank design philosophy. Wehrmacht doctrine had pursued ever thicker armor as the primary defense against anti-tank weapons, accepting weight penalties and mechanical complications to achieve protection levels that conventional guns couldn't defeat at practical combat ranges. The American-shaped charge made armor thickness essentially irrelevant within its effective engagement envelope, rendering obsolete the armor protection race that had dominated tank development since 1939. Weber's manufacturing analysis revealed equally disturbing implications about American industrial capabilities. He examined the launch tube's internal surfaces using precision measuring equipment, documenting tolerances that would be rejected at any German ordnance facility. Surface roughness exceeded German specifications by factors of 3 to 5. Dimensional variations in tube diameter measured up to 2 mm across the launcher's length. Welded joints showed visible irregularities and incomplete penetration that German quality control would never approve for military equipment. Yet these apparent defects had absolutely no impact on weapon performance. The American engineers had identified which specifications actually mattered for battlefield function, primarily the tube's ability to withstand rocket motor pressure without rupturing, then ignored everything else as irrelevant to mission effectiveness. The result was a launcher optimized for rapid production by semi-skilled workers using standard industrial machinery rather than specialized ordnance manufacturing equipment. "Look at these tolerance bands," Weber muttered, reviewing dimensional measurements with Richter. American manufacturing accepts variance ranges that trigger immediate rejection at Krupp facilities. Yet the weapon functions normally across the entire tolerance spectrum. They designed for production capability rather than engineering perfection. The philosophical difference was profound and extended far beyond simple quality control standards. German military equipment demanded precision because German doctrine assumed that superior performance would overcome numerical disadvantages through qualitative superiority. American equipment accepted adequate performance because American strategy relied on overwhelming quantitative advantage through mass production of reliable systems. Both approaches reflected deeper cultural assumptions about warfare that were now colliding on testing ranges across occupied Europe. Test Series Beta examined accuracy characteristics under simulated combat conditions designed to stress the weapon system beyond normal operational parameters. 50 rockets were allocated for systematic firing trials against tank-sized silhouettes positioned at 100-meter range intervals extending to 300 meters. Each shot would be fired by different operators selected from Wehrmacht personnel, with varying levels of training and combat experience, to eliminate individual skill as a variable affecting results. The outcomes challenged fundamental assumptions about precision weaponry that had dominated German military thinking for generations. At 50 meters, typical close-range engagement distance during defensive operations, 92% of rounds impacted within the designated target zone. At 100 meters, hit probability decreased to 78%, but remained well above the 60% threshold that German doctrine considered acceptable for effective anti-tank weapons. Even at 150 meters, approaching maximum effective range for shaped charge accuracy, 61% of shots achieved hits that would disable or destroy armored vehicles. More significantly, accuracy performance remained remarkably consistent across different operators, regardless of their military background or technical training. Experienced artillery NCOs performed marginally better than infantry riflemen, but both groups achieved hit rates exceeding German anti-tank gun standards when accounting for the time required to acquire targets and prepare firing solutions. The launcher's inherent simplicity eliminated specialized training bottlenecks that limited German anti-tank gun deployment to carefully selected personnel who had completed months of technical instruction. Richter compiled shooter feedback that revealed unexpected advantages of the American design approach. The weapon's lightweight allowed operators to engage from prone positions, offering minimal exposure to enemy fire, while German anti-tank guns required crews to stand exposed during loading and firing sequences. Absence of recoil meant shooters could observe impact immediately and adjust, aim for follow-up shots without compensating for gun displacement. Setup time measured in seconds rather than the minutes required for conventional anti-tank guns, allowing engagement of opportunity targets before tactical situations changed. Test Series Gamma evaluated reliability under field conditions approximating combat environments across multiple theater operations. Remaining rockets were deliberately subjected to temperature extremes, humidity exposure, rough handling, and contamination designed to simulate worst-case storage and transport scenarios. Some rockets were heated to 50 degrees Celsius for 12 hours, then immediately cooled to -20 degrees Celsius to induce thermal stress in components and propellant. Others were submerged in muddy water for extended periods to test moisture resistance. Several were dropped from vehicle height onto concrete surfaces to simulate rough handling during combat resupply operations. 94% successful ignition rate. The statistic made Richter physically uncomfortable as he recorded the data in his evaluation log. German percussion firing mechanisms with their precisely machined striker assemblies and carefully calibrated spring tensions rarely achieved such reliability even under controlled laboratory conditions, much less after deliberate abuse designed to induce failures. The American electrical system, consisting of simple battery, basic copper wiring, and robust electrical contacts, proved more resilient than sophisticated German mechanisms that required regular maintenance and environmental protection. One rocket failed to ignite due to corroded battery contacts after extended water immersion, a failure mode easily corrected through basic maintenance procedures. 2 rockets suffered propellant degradation after extreme thermal cycling that exceeded any realistic combat storage conditions. The remaining 50 rockets functioned normally, despite handling that would have disabled equivalent German systems, confirming American design priorities emphasized operational reliability over theoretical performance optimization. By the 3rd week of March, Dornberger's testing program had generated comprehensive performance data that would force Wehrmacht leadership to confront uncomfortable realities about German weapons development philosophy. Every metric told the same fundamental story. American industrial thinking had produced tactically superior results by optimizing different variables than German engineers considered important. The numbers formed patterns that couldn't be dismissed through institutional skepticism or nationalistic pride. Richter's final technical report synthesized 3 weeks of systematic evaluation into conclusions that challenged decades of German ordnance doctrine. The American M9A1 launcher represented not simply a novel anti-tank weapon, but an entirely different philosophical approach to providing infantry units with armor-defeating capability. Where German development had focused on building the most effective anti-tank gun achievable within engineering and manufacturing constraints, American development had focused on providing every infantry squad with immediate anti-tank capability regardless of weight, range, or precision limitations. The distinction seemed subtle but produced radically different solutions, optimized for incompatible objectives. German anti-tank guns achieved superior ballistic performance, longer effective range, greater accuracy at distance, and higher probability of first-round kills against specific target types. American launchers achieved superior tactical flexibility through characteristics German doctrine had considered secondary: immediate availability at squad level, minimal training requirements, rapid displacement after firing, and adequate lethality across all common armor targets. Weber's cost analysis provided the most politically sensitive element of the evaluation report. American procurement documents captured during North African operations indicated unit production costs of $18 per launcher, approximately 75 Reichsmarks at current exchange rates. German accounting for the PaK-40 anti-tank gun, including carriage, optics, and specialized tooling, exceeded 3,200 Reichsmarks per complete system. The Americans were achieving 90% of German anti-tank effectiveness at roughly 2% of the manufacturing investment, and they were producing these weapons in quantities that German industry couldn't approach, even if Wehrmacht leadership approved immediate production authorization. Intelligence reports indicated American factories were producing 30,000 launchers monthly, with capacity expansion continuing across multiple manufacturing sites. Ford Motor Company had converted automobile assembly lines to launcher production using the same mass manufacturing techniques developed for civilian vehicles. General Electric was producing rocket motors using industrial processes originally developed for appliance manufacturing. American industry was applying consumer product expertise to military equipment with devastating effectiveness that German precision manufacturing culture couldn't replicate under wartime resource constraints. The broader strategic implications troubled Richter as he compiled his final assessments during late March. The launcher represented more than innovative anti-tank technology. It embodied American industrial philosophy that prioritized adequate solutions, produced in overwhelming quantities, over perfect solutions, produced in limited numbers. This same philosophy was appearing across all categories of American military equipment being transferred to Allied forces through Lend-Lease programs. Sherman tanks with adequate armor protection and reliable mechanical systems versus German Tigers with superior ballistic protection, but chronic spare parts, shortages and mechanical complexity that limited operational availability. Browning machine guns with simple operation and robust construction versus German MG 42 seconds with superior rate of fire but greater maintenance demands. Thompson submachine guns with crude stamped construction versus German MP 40 seconds with precision machined components. Every comparison revealed the same fundamental pattern: American adequacy at scale versus German excellence in limited quantities. Combat reports from Tunisia and Sicily provided empirical validation of German concerns about American tactical deployment of launcher technology. Wehrmacht units were encountering bazooka teams in terrain and tactical situations where conventional anti-tank guns couldn't be effectively employed. Individual soldiers carrying 6-kilogram weapons could establish ambush positions in rocky hills, inaccessible to vehicles required for transporting German guns. Setup time, measured in seconds rather than minutes, allowed American teams to engage German armor and immediately relocate before counterfire could be directed against their positions. More disturbing were reports indicating American infantry doctrine had integrated launcher teams into standard squad organization, providing every rifle platoon with organic anti-tank capability that didn't require specialized gun crews or supporting vehicles. German anti-tank defense remained concentrated in dedicated gun companies that required careful positioning and logistical support to maintain effectiveness. American squads carried their anti-tank capability with them into any tactical situation, a distributed approach to firepower that German doctrine had never seriously considered. By early April 1943, Dornberger forwarded comprehensive evaluation reports to Wehrmacht High Command with recommendations that reflected grudging acceptance of American technical achievement despite its contradiction of German engineering principles. The American launcher demonstrated that shaped charge technology could provide tactically adequate anti-tank capability through radically simplified delivery systems that eliminated complexity inherent in conventional guns. German industry should immediately initiate development of comparable weapons to counter American advantages in portable firepower. The response from Berlin arrived within 10 days, carrying exactly the institutional resistance that Richter had anticipated. OKW Ordnance Directorate acknowledged American launcher effectiveness, but questioned whether German resources should be diverted to weapons systems that violated established doctrine and manufacturing practices. Existing anti-tank gun production was meeting current Wehrmacht requirements. Development of novel systems would disrupt established supply chains and training programs. American equipment advantages resulted from temporary industrial scale, rather than superior technical concepts that warranted German adoption. The bureaucratic deflection frustrated Richter, but didn't surprise him. German military culture had invested tremendous institutional capital in the doctrinal framework that shaped weapons development since the early 1930s. Admitting that American amateurs had solved fundamental problems more effectively than German professionals required more intellectual flexibility than aging senior officers typically possessed, particularly when such admissions implied that years of German development had pursued wrong objectives entirely. Yet battlefield realities were already forcing doctrinal evolution, regardless of institutional resistance in Berlin. Frontline Wehrmacht units, facing American bazooka teams, were requesting similar capabilities for their own infantry. Tank commanders encountering American tactics wanted comparable weapons that could be integrated into combined arms operations. Even Luftwaffe ground forces were inquiring about portable anti-tank systems after encountering American launchers during airfield defense operations in Italy. The pressure for German launcher development intensified throughout summer 1943 as American equipment proliferated across Mediterranean theaters and began appearing in Soviet hands through Lend-Lease. Deliveries. By August, Wehrmacht ordnance could no longer ignore tactical demands for comparable capabilities, and development authorization was finally issued for German versions of captured American technology. The resulting program revealed both German engineering strengths and the institutional limitations that had allowed Americans to seize initiative in portable anti-tank development. German designers immediately recognized opportunities for improvement over American baseline design. Larger diameter warheads would deliver greater penetration and improved terminal effects. Longer launch tubes would provide better accuracy through extended rocket motor burn duration. Precision optical sights would enable engagement at greater ranges than crude American iron sights allowed. Each improvement represented legitimate engineering advancement over American specifications, and each improvement introduced complexity that compromised the launcher's essential elegance. The enlarged 88mm warhead required heavier rocket motors with longer burn duration that extended flame projection beyond protective limits of the launch tube, creating backblast hazards that American design had eliminated. Precision sights added weight and fragility that reduced tactical mobility advantages inherent in simple systems. Extended tubes increased overall weapon length that complicated handling in confined spaces where close combat often occurred. By October 1943, prototype German launchers were emerging from development facilities at Rheinmetall-Borsig, visibly superior weapons that embodied everything. German engineering represented but simultaneously demonstrated why American simplicity had proven tactically effective. The Raketenpanzerbuchse 54, later designated Panzerschreck in operational service, weighed 9.25 kilograms compared to the American weapon's 6 kilograms. Length increased to 164 centimeters versus 140 centimeters for the M9A1. The 88mm warhead delivered 140mm penetration compared to American 90mm performance. Impressive improvement that came at cost of reduced portability and increased training requirements. Manufacturing analysis revealed deeper problems with German approach to launcher development. American bazookas utilized standard industrial steel tubing, basic electronics readily available from commercial suppliers, and assembly procedures that could be performed by semi-skilled workers with minimal specialized training. German Panzerschrecks demanded precision bore machining to maintain accuracy standards, specialized electrical components meeting Wehrmacht specifications, and trained assembly personnel familiar with ordnance production requirements. Early production rates reflected these manufacturing challenges. Rheinmetall facilities were producing approximately 400 Panzerschrecks monthly by late 1943, with plans to expand output to 8,000 units monthly by year's end. Intelligence reports indicated American factories were already producing 37,000 bazookas monthly, with further capacity expansion planned for 1944. German precision engineering was being systematically overwhelmed by American mass production philosophy that treated military equipment as industrial products rather than precision instruments requiring specialized manufacturing. Infrastructure. Combat effectiveness reports from November operations in Italy revealed practical consequences of German improvements over American baseline design. Panzerschreck teams achieved higher single-shot kill probabilities against Allied armor through superior warhead performance and better accuracy at extended ranges. But the weapons required longer training periods to reach operational proficiency, specialized protective equipment to shield operators from extended rocket motor blast, and more careful handling procedures that limited the tactical flexibility that made American launchers so effective in infantry operations. American bazooka teams maintained higher operational availability through simplified maintenance requirements, reduced logistical support needs, and ability to integrate replacement personnel with minimal training periods. German Panzerschreck teams achieved superior performance per shot, but lower overall effectiveness per unit time due to complexity penalties inherent in improved design. The comparison highlighted fundamental tension between engineering excellence and tactical adequacy that neither German nor American doctrine had fully resolved. The final accounting emerged through December production statistics that demonstrated mathematical realities of industrial warfare. Overwhelming qualitative advantages through quantitative superiority. German factories had achieved 8,000 Panzerschrecks monthly, representing remarkable industrial accomplishment under wartime conditions, including strategic bombing, raw material shortages, and labor force depletion. American facilities were producing 42,000 bazookas monthly from manufacturing capacity that continued expanding rather than contracting under war pressures. By year's end, American industry had delivered over 400,000 launchers to Allied forces, while German production totaled approximately 50,000 Panzerschrecks. The numerical disparity reflected deeper industrial capacity differences that extended across all categories of military equipment. American factories were producing 5 times more combat aircraft, 8 times more tanks, and 10 times more trucks than German industry, despite Wehrmacht's interior lines and captured European industrial facilities. Richter's final analysis for 1943 captured the essential strategic lesson that German launcher development had revealed about industrial warfare in the modern era. We have built a superior bazooka through engineering improvements over American baseline design. The Americans have built 400,000 adequate ones. In total warfare, their approach wins through mathematical inevitability that German technical excellence cannot overcome. Superior individual weapon performance becomes strategically irrelevant when enemy can deploy 10 adequate weapons for every excellent weapon we produce. The admission represented intellectual honesty that made Richter valuable to Wehrmacht leadership, but also ensured his assessments would be largely ignored by institutional culture, invested in maintaining belief in German technical superiority. The launcher evaluation had demonstrated uncomfortable truths about American industrial philosophy that German doctrine couldn't accommodate without fundamentally restructuring assumptions about military equipment development that had shaped Wehrmacht capabilities throughout the war. By early 1944, American bazookas were appearing across every theatre where Allied forces engaged German units. North African veterans reported encountering launcher teams during defensive operations against American advances. Italian front commanders requested additional Panzerschreck allocation to counter American tactical employment of portable anti-tank weapons. Even Eastern Front intelligence was documenting Soviet use of American launchers delivered through Lend-Lease supply channels that armed Red Army rifle units with capabilities previously limited to dedicated anti-tank battalions. The proliferation of shaped charge technology forced Wehrmacht to reconsider fundamental assumptions about armored vehicle survivability that had guided tank development since the war's beginning. Armor thickness no longer provided reliable protection against infantry portable weapons that could achieve lethal penetration at close ranges where tactical surprise prevented effective countermeasures. Tank doctrine evolved toward emphasizing mobility and combined arms coordination rather than relying on armor protection as primary defense against anti-tank threats. The strategic impact extended beyond immediate tactical considerations toward broader questions about industrial competition in modern warfare. American launcher development had demonstrated that asking different fundamental questions could produce revolutionary capabilities that traditional approaches missed entirely. German engineers had asked how to build the most effective anti-tank gun possible within resource constraints. American engineers had asked how to provide anti-tank capability to every infantry squad, regardless of traditional weapon limitations. The difference in initial assumptions had generated incompatible solutions optimized for different measures of effectiveness. German excellence in precision engineering had produced weapons achieving maximum performance per unit, but constrained by manufacturing complexity that limited production quantities and restricted deployment to specialized units. American adequacy in mass production had generated weapons delivering sufficient performance per unit, but manufactured in quantities, enabling universal deployment across all infantry formations. In extended warfare of attrition, universal adequacy proved strategically superior to selective excellence through cumulative tactical advantages that individual weapons superiority couldn't offset. The launcher represented a microcosm of larger industrial and doctrinal competitions that would ultimately determine the war's outcome. Germany's military excellence confronted by Allied material abundance. Wehrmacht, tactical superiority, overwhelmed by numerical disadvantages that accumulated across multiple theatres simultaneously. German engineering perfection, defeated by adequate solutions, produced faster than excellent solutions could be manufactured and deployed. Richter spent final weeks of 1943 analyzing captured American technical documentation that revealed intellectual framework underlying their design philosophy. American engineers consistently asked different questions than German counterparts when approaching military equipment development. Instead of "how can we build the best weapon?", American development teams asked "how can we provide needed capability to maximum number of users at acceptable cost and production rates?" The distinction in fundamental approach generated radically different solutions even when addressing identical tactical requirements. German development culture emphasized optimizing individual weapon performance through precision manufacturing and engineering sophistication that extracted maximum effectiveness from available technology. American development culture emphasized optimizing force-wide capability through simplified designs that could be rapidly produced and widely distributed, even if individual weapon performance proved inferior to more sophisticated alternatives. Neither approach was inherently superior across all circumstances, but total warfare conditions increasingly favored American methodology through mathematics that German tactical excellence couldn't overcome. The lessons learned from launcher evaluation influenced German weapons development across multiple programs during late war period. Simplified manufacturing techniques began appearing in designs like the Sate G44 assault rifle that prioritized production volume over traditional precision standards. Panzerfaust disposable launchers embraced single-use simplicity over German preferences for reusable, maintainable systems. Late war tank designs increasingly emphasized adequate capability in larger numbers rather than superior engineering in limited quantities, though material shortages and industrial disruption prevented full implementation of revised doctrine. The transformation represented more than tactical adaptation to changing battlefield conditions. It constituted fundamental philosophical evolution within German military-industrial complex that had resisted acknowledging American manufacturing advantages throughout early war years. Engineers who had spent entire careers pursuing precision perfection were learning to accept adequate solutions that could be rapidly produced and quickly deployed to frontline units, desperate for equipment, regardless of whether it met peacetime quality standards. Combat reports from early 1944 provided final validation of American design philosophy that Richter had documented through systematic evaluation during previous year. Individual German Panzerschrecks demonstrated superior performance compared to American bazookas when employed by trained crews under favorable tactical conditions. But American launcher teams appeared in far greater numbers, engaged from unexpected positions, and maintained higher operational tempo through simplified logistics and training pipelines that German complexity couldn't match despite superior per-weapon effectiveness. The mathematical reality was inescapable. German forces faced 10 American launchers for every German Panzerschreck deployed, 20 launchers when Soviet Lend-Lease equipment was included in accounting. Superior German penetration performance and accuracy advantages became strategically meaningless when overwhelmed by numerical disparities that American industrial capacity generated through accepting adequate rather than demanding. Excellent in weapon specifications. Richter's closing assessment synthesized 18 months of evaluation work into conclusions that would influence post-war understanding of technological competition in modern warfare. The American launcher succeeded not despite its crude simplicity, but because of design decisions that optimized for variables. German doctrine had considered secondary to weapon performance. Portability enabled tactical flexibility that heavy guns couldn't provide. Simplicity enabled production rates that precision manufacturing couldn't achieve. Adequate lethality enabled universal deployment that specialized weapons couldn't support. The Americans had correctly identified which variables actually mattered for infantry anti-tank capability in total warfare, then ruthlessly optimized those variables while accepting limitations in areas German engineers considered essential. The captured M9A1 launcher remained at Poltava testing facility throughout 1944, occasionally demonstrated for visiting Wehrmacht officers who still struggled to accept that American amateurs had revolutionized portable anti-tank warfare through questioning, assumptions that German professionals had never examined critically. The weathered steel tube with its simple iron sights represented more than innovative military technology. It embodied industrial philosophy that would reshape post-war understanding of how modern militaries should approach equipment development in an era of rapid technological change and industrial-scale warfare. By war's end, American forces had fielded over 476,000 bazookas across all theaters, while German production of Panzerschrecks totaled approximately 314,000 units, despite beginning development 9 months after American systems entered combat service. The production disparity reflected deeper industrial capacity differences that manifested across every equipment category and ultimately determined strategic outcomes regardless of German tactical excellence at small unit level. The lesson transcended specific technologies or particular weapons systems toward fundamental understanding of how industrial capability shaped military effectiveness in total warfare. German precision engineering, famous throughout the world for quality and sophistication, had been systematically defeated by American mass production philosophy that treated military equipment as industrial products, requiring adequate performance at high volume rather than excellent performance in limited quantities. The distinction defined not just how armies equipped themselves, but how modern nations approached the relationship between industrial capacity and military power. In the end, as Richter noted in his final report to Wehrmacht High Command during April 1945, we built a better bazooka through engineering improvements and German manufacturing excellence. The Americans built 476,000 adequate ones and armed every infantry squad in their military with immediate anti-tank capability. They won the philosophical argument through mathematics that German technical superiority could not overcome. The admission came too late to influence German strategy, but would profoundly shape how military planners understood technological competition in the post-war world. The captured launcher, serial number 43-17642, remained in German archives until facility evacuation during Soviet advance in spring 1945. Its ultimate disposition was never recorded, likely destroyed during hasty withdrawal, or captured by Red Army forces, who already possessed thousands of similar weapons through Lend-Lease deliveries. But the technical intelligence it provided and the doctrinal lessons its evaluation revealed would influence weapons development philosophy for decades after the war's conclusion, a testament to how a single piece of captured equipment could expose fundamental assumptions underlying entire military-industrial systems. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen. Now, and don't forget to subscribe.